Okay, so I want to start this video with just a quick correction on number 26. So in the previous video where I worked through number 26, I mistakenly marked iron as iron 2+. And here it should actually be iron 3+ because of the 3 with the nitrate. Okay. And the logic that I had in the last video, which is that iron's going to be more charge dense, making it a better Lewis acid, still holds up, but this will be even more dramatic a difference with the 3+. It'll be even more charge dense. So it will be an even better Lewis acid. Okay, so just a quick correction on that one. So here for number 27, they're asking us what the molar solubility of calcium hydroxide is given the KSP. So when they're asking for molar solubility, they're really asking for the X that we solve for from the ice table. So we can start our ice table. Here I have the balanced reaction. And we know that the KSP is going to be equal to the concentration of calcium ions times the concentration of hydroxide ions squared. Okay, and we don't include the solid in that expression. And we're not going to include the solid in our ice table either. Okay, so then we say we start with 0 calcium, 0 hydroxide. We gain 1x for the calcium. We gain 2x for the hydroxide. And then we can take that E rho, put it into our KSP expression. So we'll have x for the calcium, 2x for the hydroxide squared. And this simplifies down to 4x cubed. Okay, so to solve for x, we're going to set that equal to our KSP value. So we have 4x cubed equal to 5.5 times 10 to the negative 6th. So we divide by 4, take the cubed root, make sure you know how to do that on your calculator. We get that x is equal to 1.11 times 10 to the negative 2 molar. Okay, so that's going to be answer B. Okay, 28 is asking us about which isotope is most likely to undergo alpha decay. And so we want to remember what alpha decay is. And that's when we shoot off essentially the nucleus of a helium. So there's our alpha particle. And we know that alpha decay is a really efficient way to get rid of material. And so really big isotopes will do this. So anything with an atomic number greater than 83 will undergo alpha decay. So if we look at all of our answer choices, the only option with an atomic number greater than 83 is this uranium. Okay, for number 29, they want us to pick the strongest acid, and they give us Kas and Kbs. So we know that as Ka increases, the acid strength increases also. So we want to pick the option with the highest Ka. So looking at pyridine, they give us Kb, which tells us that this is going to act as a base, not an acid. So that guy's out. So we have Ka's for the other ones, and the strongest acid is just going to have the highest Ka. And that's this guy, the acetic acid. Okay. So just don't forget this relationship between Ka and strength. Question 30 wants us to find the normal boiling point of mercury. And so they give us the equation, which is just taking mercury from liquid to gas. And so we know that this phase change is going to be an equilibrium process. We know that at equilibrium, delta G is equal to 0. So if we can figure out what delta H is for the reaction and delta S for the reaction is, we can calculate the temperature. In the table, they give us the heats of formation and the entropies of formation, or the entropies for the individual species. So to figure out the overall change in entropy or enthalpy, we'll do delta whatever. Or we can do delta H. It's going to be equal to the heat of formation for the products minus heat of formation for the reactants. Okay, so we're just going to pull these values from the table. We'll use the mercury gas, mercury liquid values, and just ignore the oxygen because the oxygen's not coming into play at all here. Okay, and so we'll have 60.83 kilojoules minus 0 kilojoules because liquid mercury is its standard state. And so the delta H for this reaction is just the 60.83 kilojoules. Okay, and we can use the same process for the entropy. We'll just have delta S, and we'll do products minus reactants. Getting the values from the table, we'll have 174.89 joules minus 77.4 joules be equal to 97.49 joules. And so I like to see that these values make sense because we know that boiling should be endothermic, so we should have a positive delta H. Also, we know that going into the gas phase is an increase in entropy, so we should have a positive entropy. Okay. But do you notice how we have different units here? We're going to want to get them into the same units before we plug them into that delta G equation. So I'm going to call this 0.09749 kilojoules. Okay, so now we can take those values and plug them into this rearranged delta G equation. Say that temperature is going to be equal to our 60.83 kilojoules divided by the 0.09749 kilojoules. And that is equal to 624 Kelvin, which is E. Okay, and you'll definitely want to be careful with your units because if you didn't convert the entropy into kilojoules, you would have gotten A, for example. Okay, so make sure you're paying attention to units when you're doing these thermodynamics problems. Okay. So in 31, they want us to figure out the E NaN cell for this voltaic cell. And I think it's important to remember that voltaic cells are always going to be spontaneous. So we should have a positive E NaN cell. So we can already kind of eliminate two of the options before we do any math. Okay, and so any good electrochemist is going to start by writing the half reactions. So I know that in this left beaker, I'm going to have Al3 plus ions, and I'm going to have platinum 2 plus ions. Okay, so I've written the reduction half reactions for each of those there. So we're going to pull the reduction potentials from the tables and see which one's more positive, because the more positive is going to be the one that's reduced. So the aluminum potential from the table is negative 1.66 volts. The platinum potential is positive 1.2 volts. Okay, so this is going to be our reduction half reaction, because that's more positive, that's more favorable. And so we're going to flip the aluminum reaction, and the aluminum will be oxidized instead. Oops. Okay, so we'll have aluminum going to Al3 plus and 3 electrons. And that will now be positive 1.66 volts because I flipped the reaction, so I'm going to flip the sign. So then our E NaN cell is just going to be equal to the sum of those two values, which is 2.86 volts. Okay, so that's going to be D. And it's positive just like we were expecting. Question 32 is a follow-up to question 31, where now we use that same cell that's from the previous problem, but we're not under standard conditions. So just as a reminder, the E NaN cell that we calculated in the previous excuse me, the previous problem is equal to 2.86 volts. So because we're not at standard conditions, which would be 1 molar of everything, we're going to have to use this equation, which is from the data sheet, where we use the standard potential and then adjust for not being at equilibrium. And so we know what the E NaN is. Figured that out in the last problem. And we can use those half reactions to figure out what N is here. So this is a bit of a tricky one because it's not as clear as others. But we have PT 2 plus with 2 electrons forming solid platinum. We have aluminum giving off 3 electrons to form Al3 plus. So to balance the electrons for this half reaction, we have to multiply the top one by 3 and the bottom one by 2. And so our total number of electrons transferred is going to end up being 6. Okay, and that's one of the reasons why it's so important to write the half reactions out. Okay, and so then now we have E naught, have N. We need to think about what Q is. And Q is that reaction quotient. And it takes a very similar form to the equilibrium constants. So we're not going to include solids in this, but we'll do products over reactants. So we'll have concentration of Al 3 plus squared divided by platinum 2 plus cubed. Okay, so just products over reactants. And then we can plug in the concentrations that they give us from the prompt to solve for Q. So we'll have 2.5 squared over 0.01 cubed. We see that our Q then is 6.25 times 10 to the 6th. Okay, so now we can take our E naught cell, our N, and our Q, and plug into that equation on the top. So we'll have E cell equal to the 2.86 minus 0.0592 divided by 6 times the log of 6.25 times 10 to the 6th. And when you evaluate this, it comes out to be 2.79 volts. And that answer kind of makes sense because we have so much extra aluminum ions in this cell. So to account for that, we'll probably shift more to the left toward reactants, which would cause a decrease in the voltage. Okay, here we have the rocket fuel demo. And we've done this in lecture, and it's the thing that makes a ton of flames. And so when you have a ton of flames and fire and explosions and stuff, hopefully it's clear that this will be exothermic. We'll have a negative delta H. Okay, so that eliminates B and E. And so if we want to think about the entropy, we can look at the phases on our products and reactants. So we're starting with a bunch of solids. Then we make some gas, some liquid, and keep some solid. And so because we're taking all of the solid and making the gas, which is very entropic, and liquid, which is more entropic, this is going to become, or this is going to have a positive delta S. Okay, because we're increasing the entropy by going into more random phases, or more disordered phase. Okay, and so if we think about the delta G equation, where delta G equals delta H minus T delta S, if we have something here that's negative, and we have minus our whatever temperature times something that's positive, there's no way for this equation to ever be positive. Okay? Because you'll have something negative and you'll always be subtracting something from it. So this will always be negative, regardless of temperature. And so this will be spontaneous at all temperatures. It's a cool demo. Okay. And so with that same demo, they want us to figure out how much work it can do. When they're asking you how much work can be done, it's really getting at the delta G. So they want us to find delta G for this reaction. So let me go ahead and write the equation again. Okay, so there we have the reaction. And we'll want to keep the reaction in mind because we know we can use products minus reactants for this. So we can say that the overall delta G for the reaction is going to be equal to the delta G for the products minus the delta G for the reactants. Okay. And so on the previous problem they gave us the table of all the values. And so what we'll do is start by saying our products. So we have 12 moles of CO2. And the delta G of formation for CO2 is negative 394.4. And then we say we have 11 moles of water. And its delta G of formation is 237.1. And then we have 8 moles of KCl, and its delta G formation is negative 408.3. Again, these numbers are just coming from the table on the last problem. So we have our products, and now we're going to subtract the reactants. So we have 1 mole of that sugar, and that's negative 1544.3. And then we have 8 moles of KClO3, which is negative 289.9. Okay, and then we can evaluate that. The products, if you add those all together, end up being about negative 1.06 times 10 to the 4th kilojoules. And the reactants end up being about negative 3.8635 times 10 to the 3rd kilojoules. So we do products minus reactants and get an overall delta G. That's 6.74 times 10 to the 3rd kilojoules. And that corresponds to answer B. So don't forget, you can do products minus reactants for all of the thermodynamic values, delta G, delta H, and delta S. Okay, for 35, they want us to pick what will not change the solubility of calcium fluoride. So here I've written out the equilibrium for the solubility. And so let's go through each option. So if we add in HF, we would sort of be adding in a small amount of H plus and F minus. Okay. So if we're adding an F minus, we're going to be adding in more of a product, which would cause our reaction to shift to the left. Okay. So that would cause a decrease in solubility. So that would change it. Okay. So if we add NaOH to this solution, what will happen is we'll increase the pH. Right? And so that will change the equilibrium of F minus interacting with the water in solution to form HF and OH minus. So we're decreasing by adding in OH minus, we're decreasing how much this equilibrium can happen. And so we're keeping more of the F minus as F minus. So we would essentially be increasing the concentration of F minus present and would shift our equilibrium to the left again. Okay. Okay, with calcium nitrate, we would have it dissolve to form calcium 2 plus and 2 NO3 minus. So we'd be adding in calcium ions, which are a product, which would then cause our equilibrium to shift to the left. So that would change our solubility. Okay, with HCl, we can consider that if we have our fluoride and we add some protons to it from the HCl, it will react to form HF, which would then be sucking the fluoride ions out of the top equilibrium. So we would be decreasing the amount of products we have, which would draw the reaction to the right, and it would increase the solubility. Okay, so that would change the solubility. And this leaves us with potassium chloride. And so potassium and chloride aren't in our equilibrium. And also they're just spectators. They're not going to react with calcium or fluorine and pull them out of this top equilibrium. They're just going to float around and observe from afar. Okay, so E is the correct answer. Okay, so in problem 36 we have two iron complexes. We have one that's blue and one that's orange. So we have Fe, F6, 4 minus, and then we have Fe, CN6. Okay, so then they want us to pick what's true and what's false. The first statement says that the delta is larger for FeF6 4-. Okay, so we look at the beaker with that solution and we see blue. But if we see blue, it's actually going to absorb orange. And for that other one, we see orange, but it's going to absorb blue. Okay, so don't forget to think about the opposite colors, or the complementary colors. Okay, and so orange compared to blue, orange is a lower energy photon because it has a longer wavelength. Whereas blue photons are higher energy, shorter wavelength photons. Okay, and this energy corresponds to the gap here, this delta. The bigger the delta, the bigger the energy. Okay, and so the FeCN6 4-, since it absorbs the higher energy photon, would actually have the bigger delta. So 1 is false. Okay, for 2, it says FeF6 4- absorbs photons about 460 nanometers. And so if you look on the color wheel where it says the photon, or the colors and the wavelengths, this is actually a blue wavelength. And the 600 nanometers below is orange. Okay. And so we said that the FeF6 is actually absorbing orange, so that one's false. And 3, where it says FeCN6 4- absorbs, we said it absorbs blue, and here it says orange, so that one's false. And then 4 is saying that the delta is larger for FeCN6 4-, and that's true with what we said, because it's absorbing the higher energy photon. So the answer here is just B. Number 37 wants us to figure out the pH of an aqueous solution of 0.28 sodium azide. And they give us the Ka for its conjugate. Okay, so we can start this by icing it out. So they tell us we have 0.28 molar of the azide minus X of 0.28 minus X. We'll have 0 of these to begin with, plus X, and we'll have XX. Okay, so this reaction that I've written is a base hydrolysis. Okay, that Na3- is going to pick up a hydrogen from the water. And so what we really need here is a Kb, because this is acting as a base. But what they've given us is Ka. So we're going to have to use the relationship where Kw is equal to Ka times Kb to find our Kb. Okay, so we'll have Kb is equal to 1 times 10 to the minus 14 divided by 1.9 times 10 to the negative 5th. this equals 5.26 times 10 to the minus 10. So we can set this number equal to our expression. We're going to have x squared divided by 0.28 minus x. So we'll ignore the minus x. Multiply over the 0.28, take the square root, and we find that x is equal to 1.21 times 10 to the negative fifth. And that's equal to the concentration of hydroxide. Okay, so then we can take the negative log of that value. And that will give us POH, which is equal to 4.9. But don't circle anything yet, because it wants us to report pH. So pH is going to be 14 minus the POH. And that's going to be 9.1. Okay, so be careful with what K's they give you.